Okay, right, so the next set of modules we're going to be looking at are vectors and velocity. So a vector, as we discussed earlier in the course in the first section, is just a 3-channel item of data, very often used to describe position, location, direction, velocity, anything like that. And that's what we're really looking here is velocities. So it's possible to define how a particle is moving with a direction and a speed, and we do this with the add velocity module. So here in particle spawn, I'm just spawning particles in a torus. If I disable this, you'll see that they spawn and don't move. So this is what we've already covered, shapes and spawn rates and that kind of thing. But we want them to move, pretty boring if they don't. And so we're going to use the add velocity module here in spawn. And what this is going to do is that initial state, that first frame as you're born, we add a velocity. Now the default for this is just a linear velocity. We just reset these values. Now the way this is done, these defaults, isn't really the way I like to work. A vector or a velocity has two components. It has a direction vector and it has a magnitude. Now they have given us two things here, a direction vector and a magnitude, but for some reason they've put the direction vector at a scale of 50 and a magnitude at a scale of 1. Now it is just a kind of personal choice or a sort of stylistic choice, but it makes a lot of sense if when you're using a vector, a direction, you keep it normalized, and we can always plug this in and make sure it's normalized. Why do we want it to be normalized? Well, quite often this is data that's being driven from other places. So you might have a wind vector, and we'll talk about this later on, but you can set your wind in one place in your engine and then pipe it through to all of your materials and all of your Niagara systems and everything. Now wind is a direction, it doesn't have a magnitude, that's separate. By keeping them separate, you're always keeping things clearer and easier to understand, I think. Obviously, realistically, it doesn't actually matter. Either we do 0, 0, 50 multiplied by 1, or we do 0, 0, 1 multiplied by 50. The end result is going to be exactly the same. But in my head, directions have a magnitude of 1, they're normalized. Scales, that's how we might make things faster and slower. That's the magnitude, and so that's separate. So that would be the way that I would do this. Oops, 15. As with all modules, these can be changed, these can be random. Inputs can override other inputs. Values between 0 and 50. Now some of them are going up, some of them aren't. We can do a random direction. Now random range vector between two values. Now we're getting some moving some way, some another. All of these things, random vector will be just any direction at all, and so on. And so a lot we can do with just adding a linear direction or a linear velocity. Yeah. We can also do velocity from a point. So in this case, obviously, our torus has a shape to it, but the point that we're adding velocity from is from the center. So it's from the velocity origin here, simulation position. If I offset that by, let's say, 500 units in x, now my velocity is being added from a point here, and we're firing out kind of that way, having that down a little, maybe that's too far. And you can see we're getting that kind of coning effect as the velocity is being pushed outwards like this. Now it is always a linear velocity. What does that mean? Well, like each particle here is only moving in a straight line. There's nothing affecting it doing its path, it's just being pushed along. And all that works quite nicely. And we can obviously change the coordinate system that works with our offsets and what have you. We can also do in a cone. And so here we define our cone via an axis and an angle, or an inner and outer axis. An axis and an inner and outer cone angle. So in this case, let's try a upwards, and we'll do an outer angle of say 60 or maybe even 75. We probably won't see much difference with this because we're not using a point, but there we are. We can also change the inner. So everything's moving upwards in a sort of diagonal direction. And you can see hopefully how by combining this with the various shape modules we had before, we can create some really all the different types of movement we might want. Now this is all, as I say, single for start frame, add velocity. If I were to make this linear, if I were to move this to the particle update, well, it won't even let me add velocity. Yeah, well, let's do it manually. If I do a set new and existing parameter directly, obviously this is just data, it's just taking the velocity and adding to it. So if I go up here, if I go add particle velocity, and if I took the particle velocity and I do an add vector, input the particle velocity, particle velocity, wait, let me input that, why not? It should. So now effectively what I've created is an acceleration. And if we look, the particles get faster and faster over their lifetime. So every frame we're taking the velocity, reading it back in and adding 2 in z, reading it back in, reading it back in. And so we can create this kind of like speeding up over time. We do this with an acceleration, and we'll talk about acceleration when we talk about forces in the next set of modules. But this is effectively what's happening. So everything that's happening in here, in the update, is happening every frame, taking that velocity, adding to it. We're always adding a certain amount, and we can create this kind of motion. But as I say, we'd probably use an acceleration for that. If I turn my initial velocity back on again, we can of course scale our velocity. We haven't really talked about animation and scaling things yet much, but everything can be controlled by a curve. So all we're taking here is taking the input velocity and then multiplying it. And so scaling down a value from 0 down to 1 over its lifetime, they move up and then they stop. And so 2 ways of working really, either by taking the initial velocity and adding more to it. We could obviously kind of like, let me do it actually rather than just talk about it. If we did a multiply velocity, multiply vector by float, particle velocity by 0.98. So it's losing 2% of its speed at every frame, and obviously then eventually comes to rest, or comes to near rest. Probably doesn't ever actually come to exact rest. So 2 ways of controlling things, either choosing an amount you want to offset and change every frame, again possibly done by acceleration and velocities instead, or actually just using a curve, scale velocity. And we have a choice here of which coordinate system and things to use. So we could use a local space emitter and then scale the velocity in world space, and that would work. It would calculate the transitions between those two. Cool. Couple more bits on velocity. We'll do them in the next module or in the next video. And we'll look at vortices and what we can do with inheriting velocity from our movement of our system. Okay, so let's turn off add velocity and scale velocity for a second, and we'll use a vortex velocity. Now this is a radial movement. So we define an axis and a speed, so velocity amount, how fast are we spinning, which axis are we spinning around. In this case it's the world z, and there is a big difference between this. So we won't see a difference in this preview window, because in this preview window local space and world space are exactly the same, which is a little bit awkward because it very often hides the errors. Here again local space and world space are the same, but if I rotate this 90 degrees, our vortex force, our spinning, is now spinning around the world up axis, even though it's spawning in a ring that way. And if I change this, accidentally made that see-through. If I change this axis now, the coordinate system, to local space, it should now continue to spin around around the ring. So it does make a big difference depending on what you're doing. But yeah, pretty simple thing to use. We put in our vortex axis, we put in our origin, which in this case is our simulation position, and just which axis and how much do we want to spin around. Cool. One thing I do want to just drop back on. In our add velocity, we talked before about module, or the static mesh location module. It samples, or the outputs, if I go down to my read and writes, the writes, it's writing the sampled normal. So what do I mean? What's this doing then? Well, if I go in here and have a look, this is my model, our sort of material sphere. The point on the sphere that's being sampled, it also samples the normals away from the surface. Now if I go into my add velocity, turn this on, in my velocity direction, I can take the sampled normals, so all these will be the same data. So particles, static mesh location, sampled normal. Now this is really where it pays, or I think this is where it makes more sense to have things normalized. So the sampled normal is always going to be normalized, and now my speed is based purely on my speed. Obviously before, the default was to have that to be set with 50 velocity in the velocity vector, which I'm not keen on. But yeah, we can take the data. So we looked at it before, we were just applying position data, where we were also always getting our sample normal data. We can use that sample normal data. So if you want to add velocity in a unusual shape, you could sample a static mesh that would give you all of the velocities, all of the normals from that shape, and give you a lot of control. So using an intermediate mesh can give us a really controlled, powerful way of defining a shape. And the shape we're defining isn't just a position shape, it's also a series of normals. And so we could use that to drive our particle movement. Cool. Really nice little way of working. In this case, it's basically a sphere, but actually the base is coming up as well, and there is a bit more to it than that. So it's not just a sphere, so it is doing something. And obviously if we change our mesh, I don't know if this arrow is going to do anything interesting. Oh, it's way too many particles, that's for sure. Maybe that's not a very useful mesh. Oh, also need CPU axis. There we go. And we can see we've got the shape of the arrow and the particles kind of like always moving off it. And so quite a nice, nice way of working. Cool. We looked at vortices, adding a vortex spin. Well, let's do this for a second. We've got an error. I'm just trying to undo the things we did before. We've got an error, compilation failed, cannot compile. What's wrong? If we go to the log, particles static mesh location sampled normal was read before being set. Now if I select this, it won't give me any more information unfortunately, but particles static mesh location sampled normal, I can find that in here. Particles static mesh location sampled normal, and I can see it's being it's being written here and read here. Now I've disabled this module, and so we're trying to read data that hasn't been set yet, and it won't like that. You can adjust it and change what it does, but actually, generally this is a problem. And so if you get that error, that's what's happening. You're trying to use data that you haven't set yet. So that read before being written, what was the error? That's the error. That's what that means. Okay, vortex, we need our torus back to make this work. Now we have our particle spinning. The last one, inherit velocity. Now this won't do anything in here. Let me just set that, it's all set to defaults. It won't do anything in here because our source isn't moving. But if I go back to here, if I move this, as it moves around, you can see some of the velocity is being inherited. There we are. Maybe works a bit better. So you have a scale factor. So I'm just spawning particles here in my torus. As my torus is moving, that velocity is being implied, or being applied, I should say, to our particles. And you can see how, at the moment, that's applied at a real massive rate. Well, what settings do we have in here? There's a velocity speed, a maximum, source speed threshold to make sure that has to be moving a certain amount. But how much do we want to inherit? Well, let's inherit only 10%. And maybe let's not do it that way. Let's do one float and drive a vector with a float. And so 10% in all axes. just to keep it a bit cleaner, using one value to drive 3. And now when I move, we get a little bit of inheritance, but not very much. Quite a nice thing to add when you're using an attached particle and a little bit of trail. You want to inherit even a very small amount, goes a long way. So let's do 0.02, 2% of the source movement. Cool. Now these are velocities, as I say. The vectors describing the velocity of the particle. We can work purely with vectors, with velocities. You can scale them, you can multiply them, you can add them. That all works, no problem. But there is a better way generally of working, and that's with more kind of force-based approach. And so things like gravity, acceleration. You don't just want to scale your object's velocity down to 0 if you fire something up. You don't want to have to work out the trajectory and work out when in its path it should probably change from being an upward vector to a downward vector. That sounds like a horrible waste of time. Instead, we want to do a force to it, so fire in this direction and always come down with a force of gravity, and that's what we're going to look at next. That's going to be the forces modules. So the force modules apply to velocity, so it's still using the same kind of data sets, but the way they're applied is a much nicer way of working. Okay, I think that's everything in here. Quick recap. We can just add a linear velocity. We almost always want to have some add velocity in spawn for an initial setup, whether that's a linear velocity being moved sort of sideways or directionally, up, down, left, right, whatever the direction is. We can do that from a point in a cone, or by sampling a mesh. It doesn't work because that's not on. There we go. Or by sampling a mesh. So we can sample the normals. Obviously we can sample the velocity if the mesh is moving. Similar to inherit velocity, we can take the sampled velocity of the animated mesh and use that to define our sort of initial speed and that kind of thing. Yeah, all velocity values can just be edited and worked with as with any other data, and we can scale them and we can do whatever. And then finally this vortex velocity, really nice for doing sort of swirling, rotation and movement. And there's a vortex force as well, and we'll have a look at that and see the difference. So, okay, that's it for velocities. As I say, in the next section, we are looking at forces, but we'll do that in the next video. Okay, right, so in this next section, we'll be having a look at forces. So these work in a similar way to the velocities that we looked at previously. In fact, they affect the velocity, but they do it in a much more naturalistic, kind of realistic way of doing it. So if you wanted to do a projectile with gravity, rather than having that initial velocity, well, it's very easy with forces to have an initial velocity and some gravity, and you just get the natural curve that you want. If you're just controlling the velocity directly, you'd have to kind of have some horizontal movement and some vertical movement and then scale them and kind of eyeball it until it looked right. And yeah, it's not a very good way of working. So that's why we use forces, and they work very well. So quick sort of housekeeping. Obviously there's going to be a lot to go through here, so we'll kind of break it up and go through lots of different things. One thing I should have mentioned with the vectors, if I just drop back by one, the module here, solve forces and velocity, it was always enabled, so we never got an error, but it doesn't always exist. If you don't have it, it will not kind of solve your movement. So the way this works is you have lots of different modules that are all kind of adding to a physics force, and then finally at the end of your stack you have a solve, and that will do the calculations to work out how far the thing should move, the particle should move, based on the physics force, the engine delta time, and so that kind of deals with different length frames, and then that will output it says here particle velocity and particle position. So if you don't have it, you'll get a warning, and again, as always, it will just say here's the warning. Always read your warnings, but this one says enable the module fix, and then it'll do that for you. Or if it isn't there, it'll have add, and that will work. So as I say, if we create a new empty, it doesn't come with anything. If we add the empty from the templates, it also doesn't come with it. but you will probably just need to add a solve forces and velocity. But again, it will give you the warning when that comes up. With that said, forces can be used a bit like initial velocity. So we had before the, let's open that again. So we had here the add velocity. That made sense as a nice sort of at spawn, add your initial velocity. Well, we can do that via forces as well. But we have another module here, apply initial forces. And as always, that will give us a warning when that's not done. So for example, if I use an acceleration force, won't do anything without an apply initial forces. If I enable that, my acceleration, because it's only being applied once, it's actually working the same as a as an add velocity. So yeah, so you can use all of your forces as a sort of initial thing in Spawn. It'll just be applied once, but you need this apply initial forces module. If I pull this down, some modules we can move. We can see the big difference here. So this is now an acceleration. So they start out moving and then they speed up as the force gets applied more and more. So this would be kind of, I don't know, particles over a heat haze, over a heat grate, that kind of thing, or embers in a fire, that kind of thing, where the over time the force gets more and more applied. Okay, so we'll leave that there for this video. Basically, big thing is we need to have these two modules, apply initial forces if we're using a force module in Spawn, solve forces and velocity if we're using, well, any kind of forces or velocities in update. And we can use our forces as sort of initial things just because it's a force and it's designed to work over time. Doesn't mean we can't just use it as initial as well, as long as we've got this thing enabled. So cool. All right, in the next video we'll have a look at acceleration, gravity and linear forces. Okay, so acceleration force, gravity force and linear force. As far as I'm concerned, these are all exactly the same. So gravity is just acceleration. It just happens to be that what we call gravity is acceleration towards the center of the planet, which is usually down. And so we've got minus 50 here. If I put on an acceleration force of also minus 50, well, acceleration and gravity, they're the same thing. This gravity is just a very specific type of acceleration. And if I do a linear force, well, the difference with the linear force module is it gives me an axis or coordinate space. But if my coordinate space is the same as the gravity and acceleration, it's all the same. There's no difference whatsoever. So I can kind of understand why you have gravity as a separate thing. Maybe you want to add acceleration, that means your wind or your kind of like horizontal movement, and then gravity is your vertical movement. But I don't think there's actually any difference in these in terms of what they're doing. They all should do the same thing. One thing we can do, if we want to investigate this a bit further, with every module, if you double click, it will open the scratch pad. And so this is the module editor, I should call it really. This is how Niagara modules are built. We'll be doing some of this later on. Don't worry, we'll get into Scratchpad and building our own modules and things later. But we can see a breakdown of the module. Sometimes they're quite simple, like this one. Sometimes they're quite complex, like this one, which is curl noise, and we'll get to curl noise in a bit. But if I compare these three, gravity force, acceleration, and linear force, they are doing something slightly different, but that doesn't necessarily mean that they're doing something different, if that makes sense. They're using different nodes, but that doesn't mean that they're not producing the same end result. I have had a look. I can't really see any reason why these are providing anything different. They're doing the same thing of working with different spaces. The only difference being linear force gives you that exposed option. But we can always do a transform here, and we can transform from space to space anyway, so it doesn't really give us any extra functionality. So there we are, linear force, gravity force, and acceleration. It's probably a case of terminology and build up over time. They're pretty simple things to use. I can kind of see, like I say, gravity force making sense, because you might just want gravity, copy and paste it everywhere. That's the gravity in the world we're using, leave it there. and now we add acceleration when we want wind or horizontal movement or whatever it is extra we're doing. So it kind of makes sense to keep these two separate, but realistically they're actually just always doing the same thing. Cool. I have them here in spawn. That's not really correct. These should probably be in, can only move one thing at a time. It should probably be in update. Something like gravity is going to apply over time, and we're going to get more and more acceleration, more force building up, which is correct, which is what happens. So we'll just bring all these down. Okay, that's acceleration, gravity, and linear. As I say, as far as I'm concerned, they're all the same. So use whichever makes sense, but they aren't doing anything different, or at least they shouldn't be, because that's what they are. Gravity is a linear force. Gravity is a type of acceleration. They're all the same. I wonder if I can balance them. If I do it upwards and downwards by the same. So this is minus 50 and this is plus 50. Am I going to get no movement at all? Yes. Yes. Cool. So, yeah. All right. In the next video, we'll have a look at curl noise, which is a slightly more interesting and exciting noise, or force than the linear ones. Right, okay, so curl noise. So what we just looked at was a linear noise, or linear acceleration, I should say. But often we want things to move in a non-linear fashion. And so this is where curl noise, the curl noise force module comes into play. So curl noise is kind of a mathematically generated way of creating these kind of curly, swirly shapes, and very, very useful for natural things. So if you think about dust motes in the air, there's turbulence, there's air currents, there's gravity, there's all these forces interacting, and the end result is that things have this kind of movement to them where they kind of start in one place and they swirl around. Now this is a 2D representation of curl noise, but if you spawned a particle here, it would kind of follow these paths around and follow these lines, and you'd get this kind of movement, this motion. Very, very useful, very powerful. And we'll see all the different sort of settings and features we have with this. Cool. So here with it in spawn, if I enable it, it will just apply a value. Let me just reset these values to default. There we go. Turn that off. It will just apply a random offset or random direction to this. Because it's only applying once, it's applying in spawn. It's not that useful. It's still actually now a linear force, effectively. It's just a random linear force, which is fine if that's what you want. Much more useful, though, if we go into update. So if we follow the particle's path, maybe we'll turn on deterministic to make it the same every time. So if we find a particle and follow its trajectory, it's all completely linear. Whereas if we move it down here into update, now the curl noise is going to be applied every frame. And we're getting a non-linear movement to this. It might be a little bit hard to see with a low strength. We can put it up. And we can see, yeah, hopefully now you can see the path. And in fact, actually, we can visualize the trajectory. So we have this little icon here, enable or disable debug drawing. So I'd mentioned before that the modules have debug. So the shape modules used to be able to turn on what the shape looked like, and hopefully that will come back soon. But we can turn on the curl noise force, and it will give us the vector currently being applied. Now, unfortunately, I think there's a bug with this. Even though it's enabled here, we're not seeing the settings. But if we enable the pan noise, we get the settings. And so we can say how many debug lines do we want, how long do we want them to be. We'll scale them down a little bit. But you can see now the force being applied. Oh, it's changing every frame. And we're getting a much more realistic movement. Now, if I want to adjust this, obviously there is a strength, low value, not much force being applied, high values, lots of force being applied. But we can also adjust the frequency. And so a very low frequency noise, everything here is all being applied by sort of all the force is all being applied kind of not quite uniformly, but very similarly to everything in here. So if we imagine back with our sort of texture example, we can effectively zoom in and out. So if we zoom into a tiny little square, every particle spawning within that square all the particles will follow the same kind of path. Whereas if we zoom in, no, other way around, if we zoom out and all the particles are spawning anywhere within this image, there's going to be a lot more movement, and that's what frequency is doing for us. So here, value of 1, very low frequency, everything's following the same kind of direction. If I do something like 500, very high frequency, we're getting a little jittery movement, a little jittery noise. Probably a better alternative, although slightly more expensive, to the particle jitter we saw before. We wouldn't want to use jitter and update. You'd want to use a high frequency noise instead. Cool. Did lie to you a little. I said it was computed. Well, you can have it computed. You can have it evaluated every frame, and then it will actually calculate your noise mathematically. That's the highest quality, but the most expensive, and doesn't require any memory cost. Or we can bake it, and so we can bake to a texture. So in this case, we're using a volume texture because it's a 3D thing, but it's the same idea as the 2D texture I showed you before here in the image search. And it will just be baked to a noise. And you can pick your sort of settings for this, high, medium, or low, and it tells you the performance costs and the rough performance costs, as always, its estimates, and the memory costs to that as well. So depending on how many levels you're using with that. Cool. This is all right. This is all working, but it's not very interesting. It's all kind of following the same. If you want a bit more randomness in that noise, what we can do is we can actually move our noise. We can pan our noise field. So here, using a very low frequency noise, down to 1, go even lower, 0.1, 0.2. Every particle is sort of spawning within the same kind of position within noise. It's all kind of following the same direction, and it is breaking up a little bit, but it's not very interesting. But what we could do is we could pan our noise field, and now the whole texture is moving. And so although all the particles are moving as one, the movement that they're getting is changing over time. Hopefully that makes sense. So effectively, using our texture idea, although we're zoomed in really small and everything's spawning within the same place, the whole texture is panning and moving. And so the bit that they're spawning in is moving over time. And that gives us this kind of effect here, which is the effect of sort of random noise, but also cohesion, which is very nice. Obviously, with high frequencies, you can still pan it, it's fine, but it's not really noticeable whether that's doing anything or not, just because the high frequency noise is hiding any of that cohesion. Put that down again. Yeah, it's about balancing the numbers for the effect you want. What kind of frequency, what kind of speed in your panning. There's also nothing stopping us having 2 of these. Not Control D, that doesn't duplicate, Control C, Control V. You can have as many noises as you want, different strengths, building up kind of layers, something like that. So now it's a higher frequency, faster moving, but only a lower noise strength, and that's going to help kind of break that up. Obviously combining and stacking and layering of these things is going to build up sort of more complex movement. Maybe that's not low enough. Not high enough. There we go. It's kind of almost swarming behavior because everything's following pretty similar kind of trajectories. Cool. Last thing we can do here is a mask. So if I just remove this one, we'll just use the one here. This needs to have another force as well, or another velocity. So if I turn on a acceleration, and I'm going to put these the other way around, so my acceleration comes first. So my particles are now just being accelerated upwards and pushed upwards. And what we can do is we can mask our noise based on whether it is similar to the existing velocity. And so if I enable this, well, if I disable it first, you'll see we're moving up, and then everything's being pushed all the time, but we're still getting that overall upwards motion. Whereas if I mask this, it's moving upwards, but then when the noise does coincide and kind of does act the same as the velocity, you get this kind of intermittent noise happening. So basically, if our particle has an upwards velocity and our noise is doing this and moving around and changing directions all the time, when the two align within a certain cone value, in this case 45 degrees, what it will do is it'll apply that force, and when it's not, when it's pointing downwards or opposite directions, in this case even 90-degree directions, it won't apply that. So we're kind of getting this intermittent force where things are pushing upwards and then occasionally get blown away, which is quite nice. It works kind of like a sort of, as I say, wind. If this is a stream of particles going up under their own volition or under some kind of heat from underneath, again, little particles in a heat grate or something like that, occasionally there's a gust of wind that blows it across. And that's how this works. So if I mask it by 0, now they're very occasionally getting applied. If I did 180, they're always going to be applied. So again, you can just play with these settings for how often you want the particles to have the noise affect them. And you can see the debug lines kicking in as well. Make these a bit longer. When the force applies, you really get that debug. So quite interesting effects you can make with this, with the masking. Very powerful, lots of realistic movement. Uses a sort of curl noise, very common thing to use, and gives you a really nice kind of effect. But the most important thing, getting the frequency and the animation speed and the strength, just balancing all those numbers. Just turn this debug off. Obviously we can add some gravity in, this kind of thing. Oh, that's going to be way too high. Anyway, cool. That's curl noise. Do have a play with it. It's very, very powerful. Gets used a lot within particle systems. Just reading my notes here. The noise is very much just the shape needs to come first. Yes, if we don't have a shape to this, all our particles are spawning on a single point. Well, now the noise is affecting them all exactly the same. It's quite nice. We can get a little kind of lasso trail type thing. Really demonstrates the curl noise quite nicely, actually. But maybe doesn't look that realistic. If you wanted to vary this per particle, well, you could create some per particle randomness and do that in here, but obviously we could also just start with the shape as well. So starting with a shape, now they're all slightly different positions in the noise field and they get slightly different values, which works quite nicely. Okay, just very quickly, because it's very simple, limit force. If things are moving too fast, you can add a limit, and it just says that's too much, don't go any higher. That's not doing anything because it's not in update. It needs to be in update. There we go. Now I can say, right, well, things are moving too quickly, we'll just add a limit. And you can see that having an effect as I get down to these low numbers. Obviously it depends what forces we're adding, how we're doing things. But yeah, not something I've used very much. But it's there if we need it. Something again quite simple to do just with a set parameter. So yeah, cool. That is curl noise and limit force. In the next one, we'll have a look at the wind force. Okay, right. So next thing we're going to be having a look at is the wind force. So this is quite a complicated module. There's a lot going on, but fundamentally, the basis of it is a combination of the two things we've already looked at. So there's a linear force and some turbulence, which is here sort of set to curl noise. So it does require a drag. It says here best suited for most objects, or an aerodynamic drag, best suited for small flat objects like leaves and paper. Well, we'll enable drag for now, and we'll have a look at aerodynamic drag in the next video. So what's happening? Well, first thing we have is the wind. So we have a direction vector and a scale. Again, as before, I would do this that way around and have a direction vector just be direction, but it's the same result really at the end of the day. But we can see here we've got a force being applied in X, and if I turn the noise off, now we're just going to get that linear motion, same as if we were using an acceleration. If we do turn on the curl noise, it's just like we've applied a curl noise. So we have a very similar set of settings. We can do high frequency noise. And that will be lots of little movement like this, little jitter readings, or very, very low frequency noise. And now the whole thing's kind of moving together. This time offsets like the panning in the noise field, and we have some various settings for this. So we can do speed range, change our turbulence values over time. Now these drop-down menus, they're quite a nice new addition to the way Niagara is being built now, but there's nothing stopping us create this kind of randomness ourselves. So just because it doesn't have an option to change the input, we can always kind of create our own. So what this is doing here is speed min and max. We could always do a direct set and then do a random, and we'd still get the same kind of thing. So just because you don't see a drop down doesn't mean you can't edit and change the inputs to things. Same with turbulence. We can make that vary, so we can have a high turbulence and a low turbulence and change over time based on, in this case, the particle's age. And again, we could build that manually into that module or into that input if we wanted. Cool. So those are the two sort of main components, things we've covered already. There are a few extra settings which are quite handy. So there is some masking. Now if we enable the ground mask, this works with sort of a ground plane here with the CPU system. If you've read the note here, there are some things that only work with GPU, and we'll cover that in a second. But basically, this is doing just a height check. So where the particle is in the world, how high is it above a certain point, and then scaling the forces accordingly. So here, all these particles are spawning roughly around the 0 plane, the ground plane. But if I look in my world, you can see the particles up here having a bit more wind force applied to them, and that's just a sort of simple linear scale. So we can control what the height is and what the scale factors are, and where the ground is. We can also read the landscape. That's only for use on the GPU. It says it here, and CPU landscape uses ground elevation. So if we change the landscape, it's not going to work, it's not going to do anything. But if we go into the emitter properties and change to a GPU sim, go back to our wind force, things have changed. We've now got this world interaction setting, and if I change to landscape, it's going to give us some different values. Now if I go into all here, we can see down here we have a landscape sample, and so we can tell it to read the landscape from the world. We make this into a user parameter, and then in our user parameter we can then access the landscape. So same as we did with the static mesh location modules, the options for sourcing are source or attach parent. So you could attach your particle to the landscape, or you could just select it via source. Now I don't have a landscape in this level, but you could do that. What that will do, we'll then use the height from the landscape to do your ground distance min and max. So it's not just a flat plane. If you've got a big elevation change in your landscape, you want that to sort of be reflected in how the wind affects the particles, and you can do that via the ground mask set to landscape mode. As well as that, we have world interaction. So we can do a surface alignment. Do we want to align the wind with the surface? If you've got a big hill, the wind's going to blow along, hit that and move up. Well, as long as we're doing things on the GPU, we have access to the distance field for the world. We have access to the landscape information, and we can do some alignment and get our wind to follow that along. And then we can have some friction as well. So again, distance from the ground creates some friction, which is quite nice. So at its core, fundamentally, there are two things to this. There is a linear force and a curl noise, and then there's this extra kind of level of interaction where we're reading the data from the world and using that to adjust things. Now, this has all been built into the wind noise or wind force module here for us, but it's the kind of thing we can also build ourselves. If you're building quite a complicated system, you can grab that data, do things like wind alignment or changing heights, all that kind of stuff. And we'll cover a little bit of that later on, but it's quite nice that it's built in here. Cool. Yeah, that's the wind force noise or wind force module. say it's quite a new module and there's a lot of things it does. They've also started doing this with Niagara, which is very nice. So there's a little notes been added. Always check and read your notes and see what they do. If you don't like the little dot that it creates or this up here, you can obviously just dismiss it and it will go away. But yeah, some useful information in what the modules do to be read in those notes. Okay, right. In the next video, we'll talk about aerodynamic drag and what they do and how they interact with the wind noise here. Okay, right, so the drag modules. So we have here our wind force. So I'm just going to turn that off for a second and turn on the linear force just to get some sort of sideways motion. And the drag module, what it does is it reduces the force in your system, in your particle, sort of to represent either aerodynamic resistance or that kind of general reduction. So in a real simulation or real world system, obviously some energy is lost into air resistance, some energy is lost to sound, that kind of thing, and that's not represented in a kind of simulation in a computer, and so we tend to add a little bit of kind of a drag or damping or that kind of thing just to kind of like just reduce this energy in the system a little bit. It's a bit sort of hand wavy, but hopefully we can see if I have my drag set to 0, my linear force is being applied, things are flying off. If I put a drag of 1, we're maybe getting a little bit off to the side of the screen. Very, very high drag, we're now kind of like not getting any force at all. So here it's being kind of like applied as like a dampening. The higher the number, the more dampening that's applied. And that's my kind of general understanding of what we do with drag. Now, if I change to the wind force, it seems to work sort of the opposite, and more like a multiplier. So my drag value, if I use a very small value, rather than having no drag and no reduction, we're sort of multiplied to nothing. And if I use a very large amount of drag, it's making things slightly faster than if I have a slow amount of drag. So not sure if that's intentional or a bug. Can't see why you'd want your drag with the wind force to be different from drag with linear force, especially if you're sort of trying to use both at the same time. How's that going to work? Presumably they're sort of cancelling each other out a little bit, but yeah, not entirely sure what's happening with that. But that's what the drag module is doing and should be doing, is acting as a dampener. But the way it acts seems to be different, whether it's a wind force or linear force. So something to be aware of. We also have rotational drag, so if we're doing a rotational physics, then we can have rotational drag, and we'll cover that in a little bit. Aerodynamic drag, this works, well, also has its own dependency. This one here, align sprite to mesh orientation. So what the aerodynamic drag does is it takes the sprite, which is normally a camera facing plane, and sort of treats it like a small flat object. It says here in the tooltip, good for small things, useful for thin objects like paper or leaves. Now we'll cover the mesh orientation and sprite orientation and that kind of settings in the sprite renderer in a future video about the sprite renderer. But hopefully you can see now, rather than being camera facing planes, they're little kind of planes in the air, and the aerodynamic drag is kind of giving some rotation as well. So basically what it's doing is it's imagining it's a 3D object and doing 3D rotations, but then applying that to a 2D object to get this kind of thin flat object, which is why it makes sense for yeah, thin flat things. It does say leaves. Personally, I would always import a mesh that had some 3-dimensionality to it. Otherwise you get what's happening here. If I just reduce the rotational strength, you can kind of see how there's a bit of an area where it kind of thins out and disappears because they're all aligned to your camera. So you're looking along that very thin flat line that you can't see anything. So depends what you're doing. Can be very useful, but if we're going for a slightly higher kind of fidelity by using a 3D object of a mesh of a leaf, you can have some kind of profile to it, and we'll be covering that when we do some worked examples with leaves and things later on. Cool. In the settings there are drag settings again. I think these work like the other one. Yes, there's like a multiplier. as so, and we can add some sort of aerodynamic lift. So as objects hit the ground or come in to hit the ground, they then get sort of pushed back up again. Not doing much in my preview scene, but again here in the real world, they're kind of like, real world, in the actual level, they're being kind of pushed up now. And we can adjust our rotation strength and this kind of thing as well. So lots of settings here for how that works. So these two say work together. This is just setting up the values for the bindings in the renderer, but we'll cover that in a bit more detail when we look at the renderer itself in a future video. Okay, that's the wind force drag and aerodynamic drag. Lots of settings, lots of things you can do, but you can also just sort of use first principles and build it yourself. So a linear force, a curl noise, maybe sampling the landscape, all of that kind of thing. Cool. In the next video, we're going to be having a look at point attraction and line attraction. So next set of forces, yeah, in the next video. Okay, so the next module we're going to be having a look at is the point attraction force module. And what this does is attracts all of the particles to a single point. As with all the force modules, it works in both spawn and update. And you can see here it's just applying an initial pull inwards. Now there is a radius, which is why the outer ring of particles isn't being attracted. And if we up the radius, obviously that will now pull everything in, and we can adjust the force as well. There is a fall off, so the further away a particle is, the less force gets attracted. Now in this case, because it's being done in the spawn, it's just that initial force. It's not really doing that much, but if we put it here in the update, we'll see a much more kind of like things being pulled into the center. Now we have a particle kill here. This works in update, doesn't work in spawn. And we can kind of see, if I put the strength up a little bit, particles are going to kind of go through the center and out the other side, which might be what you want. That might be fine. So although we've turned on the kill radius here, or the default is this to be turned on, it's not working because it's in the spawn section. But if we move that to update, it would, or it will. And so now particles getting killed with a radius of 4. So 4 units, anything within 4 units is getting killed off. Now, we can also do that directly with a kill module. So there is a kill particles in volume module. You can specify the shape and the radius. We've already talked about shapes. And there we've got a kill volume enabled, and there's options here to invert as well. So that's just going to kill everything because nothing starts inside it. But yeah, there's options for that. Cool. Quite a simple module, quite a useful module. We can control what position to attract, where we're attracting to. In this case, we're attracting to the center of the simulation. That makes sense. That works. No problem. And we can have an offset, and we can animate that and that kind of thing. So a lot of control, quite useful for doing that kind of magic orb, things pulling in towards the center, all being done with a point attraction. Yeah, very powerful module, very useful for doing this kind of thing. Obviously, if we use a negative value, we can do repulsion. That works as well. So you could make kind of a star field or some kind of energy engine pushing things outwards. If you want to push things outwards in a kind of radial manner, you can do that. You can just do a point attraction repulsion, or point repulsion force, I should say. And yeah, that all works very nicely. Obviously, as with all of these things, we can just do random values. So now if I do 5, say -5 and 5, something's pulled in, something's pushed out. Adjusting our values in Niagara. To do whatever we want. That's a bit weird. That's the other way. I wanted a large value and a small negative value. So most things really sucked in, some things pushed out slowly. Whatever it is the effect that we're trying to make. And here we are. So point attraction force, pulling things into the center either as a just initial force into the center or as an actual force in update. So now things are being accelerating into towards the center. Kill radius, stopping particles, overshooting, and there's overshoot correction as well. So if particles are moving very fast and our radius is too small, they might go through. Can't actually do it. Maybe larger values. Not too bad, but that's what the kill radius overshoot correction is doing. Always catch very high speed particles would otherwise overshoot the kill radius in a single frame. But yeah, you'll see that when it happens. Cool. That's it for the point attraction. In the next video, we'll talk about line attraction. Okay, so the line attraction force is similar. Works very similar. Turn this first one on here. Rather than attracting to a single point, though, it attracts to the nearest point on a vertical line, or a line defined between 2 points. It doesn't have to be vertical, it just happens to be so here. Let's turn the kill volume off. Maybe we'll keep the kill volume. Yeah, I'll keep the kill volume on. I suppose it's not doing anything because it's not a kill volume, it's a cylinder, it's a kill volume sphere. Well, fine. Anyway, we've already covered kill volume. So what's happening here? Well, we've defined 2 points, in this case plus and minus 50 in Z, and we have an attraction strength, and that's it. It's just pulling in towards those points. There's no attenuation radius. If we wanted that, we'd have to build it ourselves. Just taking the current position and then a sort of center point, getting a distance, using that as a scale factor. Easy enough to do. You can check how the point attraction force does it. Don't know how complex a module that's going to be. Here we are. That's the fall off. That's the section you want. But you can build that into your module if you want. One thing to note though with the line attraction, the values here. If I turn off local space, these particles are in the world. These values, though, are in world space. So it looks nice here because the local space and world space coincides. But if I minimize and look in the real world, we'll say the gameplay level, it's pulling towards plus and minus 50 in world space. And so that's not giving us the same result. And that's why. So it's always, again, really good to have a viewport open. If you've got multiple monitors, it's possible to have multiple viewports. Viewports. So I've got 2. One of them is over here on my second monitor, as well as my content browser and a second details panel. Very useful. So you can always refer back to what's happening. You can always see kind of the real world. I keep calling it the real world, the game world, on your second monitor when you're working here in your Niagara system. But what you see in these 2 viewports obviously is not correct. Easy fix is to change it to local space. Now those values in the line force are in local space. But if we don't want to use local space, we wanted to have this attached and wants to be like trailing particles, we can do some conversion instead. So that's what this second one is doing here. So line attraction force, you can do a transform vector. Transform meaning to change from one space to another. If we take our 0, 0, 50 and we change from local space to world space, now we have a non-local space emitter. So as I move this around, it's now going to be dragging in and pulling towards that line, but the line is defined sort of locally to the system. And there's a few ways we could do this, but this transforming works very nicely. Obviously, if this was in local space, and let's just put the correct line attraction on. So now we're local space, and when I move this, it's just moving and pulling in towards. The whole thing's just moving as one, which doesn't look as nice, I don't think. Depends obviously what we're making. But if I turn local space off, but I convert my values to local space, we can get this kind of trailing attraction kind of thing happening, which is quite nice. Cool. That is the line attraction force. Tracks the nearest point in on the line, and yeah, just be a little bit careful about your spaces. And say, when you're working in this viewport, things can look great and work fine, and then as soon as you put them in the game world, they don't, and that's generally because local and world space are not the same between the two things. Here in the viewport, local and world space are the same. So there we go. Okay, right, next one we're going to have a look at is the spring force, which is down here, I think, in our update, but we'll do that in the next video. Okay, so the spring force, right. If we enable this, now I have adjusted this, and we'll reset it in a minute back to default, but just to see what it's doing first. Spring force, a bit like a point attraction, but one of the properties of a spring, rather than having the attenuation radius and sort of like a maximum distance that the point attraction has, a spring, the further away you are, the more the force that they try you to use to sort of bring you back. So the sort of restitution force. So you get this kind of effect. So it's not possible to have your particles kind of leave the spring, whereas with a point attraction, it's around a certain place. Particles outside of that radius aren't going to be affected. Now, just to reiterate my previous point about local and world, this looks great, no problem. If I go to the world, well, the force is obviously over here. It's doing things in the wrong axis system. We could go in and change the positions. I'm just going to turn this on local space for now, and now that's all working perfectly again. So very interesting. Of course, now as I move this around, it's not really doing any kind of animation because the whole thing is all stuck in local space. It isn't necessarily what I want. If I just disable this, let's create a new one. New spring force in world space. There we go. Default is just to drag in to the center. So the settings we have in a spring force: force strength, how strong is the force pulling it in, where is the equilibrium position, so what are we pulling towards, spring tightness. Tighter values are going to pull in quicker, low values are going to do be much slower, and then we can kind of do velocities and dampening and that kind of thing. And this is really nice. So now this is particles in world space, and they're attracted to a point. And as I say, the working like a point attractor, pulling in towards this point all the time. But when you're doing that, you're unable to kind of like detach the particles. If this was you're trying to do a similar thing with a point attractor, you'd struggle because at some point you go outside of the radius. So it depends what you want. Depends what effect you're trying to create, but quite a nice way to have particles follow a point. Cool. So all in this one, I just animated the attraction point between two positions, but obviously those positions are in world space, so we'd have to do that same thing of transform to local. And if I find the force that was doing it, line attraction force here, with any input we can click and copy paste, and we'll do the same with the other one as well. So the line attraction force 0, line end, copy, spring force, and B, paste. Can get quite confusing. Obviously there's a lot of inputs and outputs. Unfortunately, it's a very powerful system. There's a lot of things going on. It will sometimes just have a lot of information and data to the UI. But now I've converted my my offsets that it's animating between, but it's also still in world space. So I can move those values and move that around. So you can always combine things and adjust things and whatever settings you need. Would work very well with a little animated emitter on a loop, creating some really quite complex motion as the particles are following a point that's also moving. And in this case, they're doing their own movement within the particle system, and also I'm moving it within the world as well. So some really complex motion happening here between the two things. Cool. That's it for our kind of point attraction, line attraction, and spring force, which is a bit like that. In the next video, we're going to have a look at vortex forces and then finally vector noise, and we'll be done with all the possible forces that we can use in our systems, but vortex force in the next video. Okay, right, so getting to the last couple of forces now. Vortex force. We saw vortex velocity in the previous section. Let me just open that one. So vortex velocity, rotation and movement around a point given a speed and an axis. That's great, but actually if we think about how vortices work, as well as having a rotational component, they also have a kind of outwards motion as well. So here, same idea. If I do my vortex force, let me just reset this to default. So the spin is happening, but the spin's also pushing particles away from the center. So this is more of kind of like a whirlpool or a spinning, I don't know, Catherine wheel, that kind of thing. And we've got choices for this. So we've got how much spin is there, what's the force involved, which axis. So we can spin around any axis, as always, local and world, worth thinking about. In this case, we've got an option, simulation and local world. Simulation, what that will do, we'll use the whichever's been specified here. So you can use what the emitter properties tell you, or you can use specifically local or world, regardless of what the emitter properties are telling you. And that's what the three options are there. And we are vortex force. Vortex origin, again, in this case, it wants to be in, if this is not in local space, and this is the, well, it's always using the simulation position. If I change this to, let's say, local 0, local value 0 looks correct here, but obviously isn't correct here because it's using the world origin. So again, just very common, very easy thing to get wrong, dealing with different spaces, which is why using, I guess, simulation position works, because that will be converted whichever space. Origin pull. So here, if we want to counteract the force pushing things outwards, we can create a pull amount, and that will pull things inwards. Obviously, we need to try and sort of balance that. That's pulling in too much, going outside. Yeah, depending on what you're trying to do. If you do just want that radial spin, obviously it's much harder to balance this. So the vortex force, no, the vortex velocity will work nicer for just that sort of spinning around a point, or rotating around a point, I should say. If you want this kind of spin and outwards motion, then you'd come from vortex force. As with all of these, if it's a force or a, if the force is applied in spawn, it'll apply once. If it's applied in update, it'll apply every frame. And now we're getting more of a kind of thing. If I put that pull amount now on, that will probably work better. So I'll be able to sort of try and pull them in to the center. Yeah, should be able to find a value where it's kind of an equilibrium, where the outwards force is equal to the inwards force. But struggling a little bit. Maybe some drag will help. Something like that. You could always scale your inwards pull based on your outwards distance. Something like that's kind of working. That's sort of a donut without anything flying off or pulling in too much to the center. But you can obviously fiddle with these values to your heart content to create the effect that you're trying to replicate. But that's the vortex force, similar to the vortex velocity, and that you have a rotational value, an axis. But in this case, it says it has a push or pull value. Obviously, negative values will push outwards. And so, same kind of thing, kind of attracts or combines a radial motion and a point attraction as well, which is a bit more physically accurate. Okay, right, last one, vector noise force, and we'll have a look at that in the next video. Okay, right, so the last one of the forces, vector noise force. Add a random noise to things. Default it's very high, bring that right down. We're just adding some random movement. So adding a random amount of noise, in a random direction. In this case, it's in spawn, so it's just happening once, and we're just getting things moving out in different directions. If I put this in update, well, it's still applying, but we can also have a random noise time interval. And so we can say, right, I want you to add this much force, and then every so often, it's going to add another force. And this is kind of doing the same kind of thing as a curl noise. There we go. And you can see every second in this case, the particle gets a new force and moves around. But it's not as nice as the curl noise. It's not a nice smooth motion. And so this is a slightly more optimized, probably slightly cheaper way of doing it, but you don't get as nice a result. And to be honest, these days, if we're doing GPU, we'd probably just use a curl noise. But it's there if you want it. Note, nothing starts moving. If we did want that to come through, remember the interpolate spawning. Interpolate spawning on should fix that. That's interesting. That doesn't do that. But so it's not doing a sort of a tick on the first thing. But we could always take this and then have it duplicated in both places. It's not the nicest workflow, but that would work. So they'd spawn, pick up the random noise, and then no. Let's turn that off. Spawn, pick up a random noise. For some reason, the scale's very different. There we go. We could spawn, pick up a random noise, and then have the other noise kick in as well. So if it's already in motion in update, this value is quite high, but the initial value is quite low. They look about the same. So I'm not quite sure what's going on there with the different values, but visually we got the result we want. We spawn moving in a random direction, and then after a second we kind of tick and bounce. And but as I say, I wouldn't really use this. I would use curl noise. And if I did want a random initial noise, I probably wouldn't use this either. I would just set new parameter directly, and we can do initial velocity, particle velocity, and we'll do a vector by float, random vector, and then, well, there's a scale value in here, and that's the same thing. So once you get into the workflow of using Niagara, quite often, rather than using the module that exists, you'll just program the value yourself, just because it's easier and you know how that works. Okay, right. That is it for forces. I believe if I type in force, we've been through every single one of these. We'll worry about these things later, maybe. Yeah, it is a much nicer way of working than just working with velocities directly. Scaling velocities, you could create the arcs you want and the motion you want, but generally it's easier to apply some forces. And there's lots of options depending on what we're doing. So attraction forces, repulsion forces, vortex forces, wind forces, picking up things from the world like the terrain, all of that is doable in creating the motion of our particles. And we can also obviously combine these things as well. So there's nothing stopping us having a vortex force, or let's say vector noise, some acceleration, gravity. Let's do wind, drag, spring, all of these things. And it will just combine them all together. I guess here the spring force is probably killing most of the other movement. But depending on what you're making, gravity, wind, acceleration, all of these things can obviously combine together quite nicely. Let's do it that way. To create the kind of motion and movement that you want. So up to you. Cool. That's it for forces. Next thing we're going to have a look at is rendering. So far we've looked at overall properties, where our particles spawn, or rather how many particles to spawn, where they spawn, how they move, and now we're going to move on to what they look like. So we're going to do sprite rendering, mesh rendering, ribbon rendering, other renderers, and then some other details as well to finish off as well. So next video is going to be sprite rendering. Okay, right, so as I said, so far we've looked at, maybe let's kill the force on this one. Just don't want this to be flying off all over the screen. There we go. We've looked at particle properties, how to spawn particles, where to spawn particles, how the particles move, but we haven't done anything with how the particles look, and so that's what this next section is going to be about. So in this case, we're looking at sprite rendering. So a sprite is a 2D quad. What do I mean by that? Well, let me just start with a new sprite renderer. Oh, that's animating. Let's turn that off. There we go. What do I mean by a 2D quad? Well, if I go to a wireframe view, you can see that it is a quad. It's a square. Doesn't have to be exactly square, it can be rectangular, but it has 4 sides. That's why it's called a quad. And it has 2 triangles. That's what it's made of. And as we move the camera around, it is camera facing. Now, it doesn't need to be, and we'll have a look at those settings as well. But that's a default sprite. It's a just a plane. The fact that it's camera facing means we never see the edges, like the flat edge we briefly saw in the aerodynamic drag lesson. And it allows us to do this kind of like illusion of volume. So if I rotate around this, because it looks like a sphere from every angle, we understand that, our brain reads that as a spherical object. It's not a spherical object, it's a flat plane with a picture of a sphere on, but it looks the same from all angles. And that's the sort of nature of sprites. We've been using sprites in games in real time for a very long time, and we will continue to do so. They are very cheap, they are very good at doing what they do and creating the illusion of something facing us with some volume. As we sort of start to get the ability to do real-time fluids, we might start to move away from this, but unfortunately the hardware we currently have isn't really up to the task of doing real-time fluids and anything else at the same time. So you can have some very nice real-time fluid tech demos, but you try and put that into a scene with any other kind of environment and world and characters and gameplay, and you very quickly run out of performance. So for now, we're still using sprites, and there's a lot we can do with sprites. So for example, if I apply the explosion material, so this is from the starter content. If you haven't done my materials course, I do recommend it, but we'll quickly cover what's happening here as well. There's way more depth than what we cover there, but this is a flipbook. So a flipbook texture, named after sort of animation techniques. You do a different frame on every page of a book, and then as you kind of scroll through the pages, you get an illusion of animation, and that's called a flipbook, and that's a thing that animators use, and it's a thing we use here in real time as well. So this is a 6x6 flipbook, 6 frames horizontal, 6 frames down, 36 total. Generally, we work with sort of 4x4 or 8x8, those kinds of numbers. The more frames you have in your animation, the smoother it is, but the more space it takes up in the texture, so the fewer pixels per frame. So this is a 2K texture. Because it's 6, the number of pixels wide here is not a very nice number. It's probably fine, but yeah, each of these pixels or each of these individual image isn't that high resolution, and we just can't afford to have super high resolution images and also many frames. So 36, 64, what would it be, 16, those kinds of numbers work depending on what we're making. So explosions tend to want to have quite a few frames. Things like smoke maybe can get away with a few less, but it all depends. So this is the technique we're using. So we've taken, in this case, it's a rendered footage, I believe, of an explosion happening, and then they just like animated or captured every frame, taken it out, and we've plugged it in here. So this is the particle sub-UV node. It's not just a texture sample, particle sub-UV. This allows us to do what's called frame blending. So when we play our animation, we're not just going to get this frame and then this frame and it's going to sort of move. It's going to sort of do some crossfading and blend from one frame to the next, and you get that here, and that's only available if you're using a particle sub-UV sample rather than a texture sample. There we are, blend. This is this option here, whether we want to blend what's called crossfade. So as one frame's blending in, next one's blending out, and that just helps to smooth out the animation, which works because we've only really got 36 frames of animation here. Okay, So if we plug that into our sprite renderer here, what we can see is obviously all 36 frames, which isn't very useful. We need to do some settings and some edits to this. First thing I'm going to do is set up our sub UV. So we can enable our sub UV blending. That's the same as I just said and before of this sort of crossfade. And how many images in our sub image? So sub image meaning just kind of part of the bigger image. Well, in this case, it's 6 by 6. We can see that. And now we're seeing just the first frame of our explosion here. Cool. If you want to see the animation happening, there is a module called sub UV animation. And what this does will blend between the frames. And in this case, we want to have a linear blend. That's fine. We want to use the sprite renderer. We need to tell it which sprite renderer. So in this case, we're using the second one. And there we are. We now got our explosion. There are some options in here. As always, we can change from just a linear blend, let's say, to a curve. And now what we're going to get is a faster explosion at the fast because our curve is faster. And then a slowing down at the end, and we actually see some kind of stuttering happening at the end there. So maybe if we move this across, that will work a bit nicer. Obviously, we can adjust our tangents. We don't really ever want it to be going back on itself. That doesn't make any sense. But you can now draw an animation curve for that. And maybe there's a bit smoother, which is quite a nice way of working. We can do purely random. So some flipbooks might be built in a way where you can randomly jump from frame to frame. That's not the case here, but that's what that does. You can have an infinite loop. So now it's going to go through, and rather than just sort of playing through once and then stopping, it's going to go and play and play and play and play. And we can choose how many loops per second. And so let's say 2 loops per second, faster, faster, faster. This flipbook is designed in such a way that it goes from, where are we? Frame 1 to frame end, whatever it is, 36. And it's only designed to do that. So it's got a very specific animation in it where you start at this end and you end here. I don't think, I just have a look. Oh no, we've got some. Here we go. If I open up this one, this is a fire texture we're going to be using later. This is designed as a looping texture. And so within this texture, it doesn't really matter where you start. It doesn't matter where you end. As you go off this frame here, we come back on this frame here. So this is based on a simulation. And then it's just been sort of photo manipulated or video manipulated so that as you're blending off, you're blending in. And this allows us much more reuse. So for anything that's a kind of looping flipbook, we'd want to, if every fire kind of spawns and then bursts and then dies, it's going to get quite repetitive. Whereas by using a looping one, we can randomize the start frame. And we have an option for that here in our UV animation, sub UV animation, random start frame. And now it's going to randomize the start frame. I wonder if I can just find that fire material. Okay, so the material immediately breaks. Why is that? Well, it's a 8 by 8, not a 6 by 6. So if we plug in 6 by 6, it's not going to work because the size of the frames are wrong. But we can just update that to 8 by 8, and there we are. And it is a looping effect. You can kind of see a little bit of pop every now and again, and that's just the sprite restarting. Maybe we'll add a color scale on that. So if we scale our alpha, float from curve, and we'll just fade in and out. And there we are. So each time the particle spawns and scales in, it's a different frame in the animation because we're using that random start frame. So if we look at this for a few seconds and just watch it loop, that little lick that happens here at the top right, it's always the same lick up here, not very nice. Random start frame. The lick happens, but it doesn't always happen in the same place. And so it's a nice slow way of breaking up your repetition in your sprites and your sub UV. Okay. That's, I think, enough for the quick introduction in this video. So if we're using a flipbook, we want to use sub UV. and then with the sub-UV animation module, we can pick what we want to do with that. So do we want it to be just a linear playthrough, random start frame or not? Do we want to use a curve, infinite loop, or we could just directly specify which frame do we want. That might be useful for certain things. Interesting. There we go. You can definitely get different frames in our material. So yeah, very powerful, great way of working. We use flipbooks and kind of animations baked to texture all the time, as you can see, for things like fire animations, explosions, stuff like that. It's way too expensive to simulate that stuff in real time. So at least for now, it won't be forever. But there we are. So sprite renderer and sub-UV and sub-UV animation. In the next video, we'll look at some more settings in the sprite renderer. Okay, so we've looked at the sub-UV settings. Next thing down here on the list are particle cutouts. So these are a great way of working to reduce overdraw. So if I have a look here, we have our sprite. In this case, like I say, 2 triangles, simple quad, and it is using the whole frame here to render. If I turn on the complexity view mode, shader complexity, you can see the whole square is being calculated. So it doesn't matter that only the center bit has fire in it. It's using the whole thing. It's not very efficient, and we can fix that. So we can use what's called a particle cutout. Now, if I load in the same flipbook texture here as being used here, and this is the fire square, I believe. What the engine is now capable of doing is taking the outline of the frame that's currently rendering and then working out how to move the verts, and in fact make more verts to kind of really contain itself to that space. And I'll show you how that's done. So we have to tell it which source mode to use. Default is the alpha, but if I open this texture, this doesn't have an alpha channel, so it's not doing anything. If we change this to either color brightness or one of the channels, let's say red, what we'll find, if I go back to my outline here, you can see the outline of my sprite is now really, really tight. It's really close on what's being rendered. And if I go to the shader complexity again, you can see we're really saving that value. So one of the very big performance hits of using particles is what's called overdraw. And so layers of transparency, if I have multiple layers on top of each other, and if I just make a few more of these, let's do it that way, you can see as more and more layering, I'm just creating duplicates and layering them on top of each other. By doing that, we're adding in more and more shader complexity. If I go somewhere like this for the sort of like 3/4 view, there's only little bits of overlap. Whereas if I disable my cutout, just use that, you can see there's way more overlap. So using a much smaller shape, in this case 8 vertices or 4 vertices. Oh, that hasn't worked. Why has that not worked? Just need to recompile probably. No. Interesting. There we go. The undo didn't refresh correctly, so I just had to reassign it. But yes, using 8 verts or 4 verts, depending on what works. Generally, more verts will give you a closer attachment, and paying a little bit more for more vertices is cheaper than paying for more overdraw in your pixels. So there is an option here for use material cutout texture. What this should do is read the material and get the right texture. Now I've had problems with this, doesn't always work and doesn't seem to work here, so not quite sure what that's supposed to do, or at least I think that's what it's supposed to do. Use the cutout texture from the material opacity mask. Okay, fine. So my workflow tends to be that I don't use a opacity in the texture. I just multiply the color into the emissive color. So maybe we'll try the other material and see if that works. So if I use the explosion, let's check the material first. So the material here does have an alpha channel, but again, the alpha explosion isn't plugged into the alpha of the opacity texture. So generally with things like fires and explosions, you use emissive rather than translucent, and so you don't need an alpha, you just use an emissive. And so that setting, wherever we were, the use material cutout texture doesn't really work because the material isn't built with the texture in the opacity. Use the cutout texture from the material opacity mask, or if none exists from the material opacity. Yeah, so that's what that's intended to do, but at least the way that I tend to work, it doesn't work because it's not set up that way. But we can always plug in the texture directly. And there we are. And now we have our particle cutouts. Cool. That's what particle cutouts do. That's how they work. They are definitely worth using. Very rare you would use a square for anything except tiny little things, because it's just cheaper to cut those edges. Yeah, using a particle cutout. Okay, in the next video we'll have a look at some of the more settings in the sprite renderer. Okay, so next I'm going to have a look at in the sprite renderer is the custom facing vector. And so currently we have a camera facing sprite. If I go to my settings, we have a facing mode currently set to automatic. Now there are lots of options within here. Face camera plane. Very similar. Sprite billboard plane is completely parallel to the camera plane. Looking at the camera origin, trying to keep its axis aligned to the camera's up axis. Okay, so if you have kind of cameras that can rotate and tilt, then that would be a different option for you there. Face camera position. So it's facing the camera position, but not the camera angle, and you can see we get some flipping over the top there as the camera kind of goes over the top. If I do face camera and go over the top there, that's not going to happen. So a couple of options. Generally, if we're doing face camera, we're just doing face camera. But what is interesting is this one here, custom facing vector. Now what this will do is nothing, because we need to set it up elsewhere. What this will do, we'll use the custom facing vector binding. So down here in bindings, all the renderers have these. It's a very sort of common way, or kind of like repeated way of working with Niagara. Basically, these are the values that or the parameters that we're editing. How are we editing them? What are we doing them? Well, we're plugging in a parameter, and we can change what parameter it is. So basically, it's hooking up two things together. So this one is using the custom facing vector. And it says here particles.sprite facing attribute. So particles.sprite facing, not custom sorting, not camera thing, sprite facing binding. That's the one here, sprite facing. So we can set that ourselves. Set new or existing parameter directly. Sprite facing. And if I set this to be X, we have a look at our sprite now, rather than being camera aligned, it is facing a certain direction. In this case, it's facing the x-axis. Now this is pretty commonly used with world up aligned particles. So if you have fog on the floor, or a kind of shockwave and that kind of explosion, you generally do that flat. Oh, at least you can. It's an option, and that's done this way with a sprite facing. So the facing mode is set here. The binding tells you what it is down here. Unfortunately, the naming's maybe not the most consistent, but you can always go and look up what it is. And if this doesn't exist, it won't do it. And so it's just still going to fall back to being camera facing. But if you do want to add that, we can add a sprite facing thing in there. Similarly, we can do an alignment. Let me just turn off that. So alignment wise, we can do a custom alignment. So we can do velocity aligned. Let's do that first. That makes sense. So if we add some velocity, so now our velocity is being added in the x-axis. Should probably be consistent, shouldn't I? There we go. And we want our particles to follow the direction of travel. They want to follow their velocity. And to do that, all we do is set them to be velocity aligned. Note that the top of the sprite in texture space, so up in texture space, is what gets aligned with the velocity of the sprite. So generally, yeah, it just depends how you're making your texture. But if you are doing velocity alignment, you want to do up pointing. That's going to be the velocity alignment. Obviously, if we add something like gravity, let's not do just a little bit of gravity, -50 maybe. That alignment's going to change as the velocity changes, and they're always going to follow. So it's very useful for directional elements. So sprites, sparks, and things like that would be velocity aligned. Radial things that fire outwards from a point, or anything like that, we can use velocity alignment, and we use it all the time. Now it's also camera facing as well as being velocity alignment. So as I rotate the camera around, it's always trying to face me. We do get this kind of effect here, where the camera is sort of aligned with the sprite. You get this sort of weird edge. You can see the spinning, and generally we'll just use a Fresnel to remove that in the material. So as well as velocity aligned, we have custom alignment, and if we have a look at the alignment binding, sprite alignment, we can do the same thing here. So we'll add a sprite. Oh, sorry about my dog. I'll sort her out in a second. So if we do our sprite alignment, now it's aligning, and we can align to say, that's sprite facing, sprite alignment, and we can align to a certain thing. So we're now aligning to the smooth velocity, aligning to, and smooth gravity as well. So in this case, we're aligning to Z. What this means is I go over the top, it's now going to disappear. So it's not doing camera facing, it's camera facing on the other axes, but as I move over the top, it's disappearing. Rather than setting these directly, there is a module, sprite facing and alignment, where you can set these, and you can set your coordinate system. So if you're old school like me, you just set it directly. If you're new school and you want to use the module, there's a bit more setting to that. You can just create the module there, but this setting here also needs to be correct, or kind of align, or kind of work in synchronous, work together with the settings here in the sprite renderer as well. Oh, I see. So if you set it to automatic, it will do it if it exists. So that's presumably the default. Yeah, we are. So with the default set to automatic, it's looking for the sprite facing binding. If it exists, it uses it. If it doesn't, it does camera alignment. Can't see anything here now. It's probably aligned to the wrong thing. There we go. There we are. So sprite facing and alignment. This is what we mentioned before with the aerodynamic drag with the flat planes. They would be controlling the sprite facing and sprite alignment vectors. And it's useful. You can do velocity alignment, flat alignment, all of those kinds of things, just by controlling those values. So cool. In the next video, we'll have a look at the sprite rotation. Yeah, we'll do that in the next video. Okay, so talking about sprite rotation. Well, actually, we probably should have started here with initialize particle. There is some sprite settings for initialize particle. We covered them back in the first example, in the first module, but just to reiterate, we have uniform, which is a square, so each side is uniformly the same as the other. We have a random uniform for a min and max size within that, so 50, 150, but randomly sized, but it's always a square. And we have non-uniform as well. So here the x value is the width, y value is the length, and we can see now we've created a long thin sprite. One thing that we can't edit here, but we can edit in our sprite renderer, is the default pivot in UV space. So where the sprite aligns itself to the particle. Now by default it's 50-50 or 0.5-0.5. So the center particle, or the particle here that's spawning at the origin, the plane is aligning itself to be in the middle. If I set this to be 0, 0, we're now aligned to the top left of the square, 1, 1, bottom right. And generally we don't mess around with X, but what we do is this, setting the flame now to be based on the ground. Very useful. Oops. To be able to sort of adjust that so the particle spawns at the ground and the sprite only comes upwards. very useful. Obviously it would work the other way as well if you wanted to go down, default being halfway up. Okay, now I mentioned rotation. We have a rotation mode here, full random rotation, or direct set in degrees, direct set by normalized angle. We covered these before. Works very well for a full random value, or whether we want to use 45 degrees, which would be the same as 1/8 of a rotation. So depending on how we want to define our rotation, there's two different options, but they're just a proportional calculation kind of thing between the two. But there's no rotational mode, rotational rate to this. So there's different rotational mode here for the initial rotation, but not any rotation over time. But there is a module for that. So here in particle update, we type in rotation, sprite rotation rate, and we have one already. Now this will rotate our object. Now the values of this looks like it's in degrees per second. Not entirely sure. I set that to 360. Yeah, there we go. So 360 degrees per second. So actually, well, I suppose it's the same as one of the two things in here, but depending on what we're doing with rotation, you tend to use, there's radians, there's degrees, there's normalized. They all define the same thing, but obviously different numbers. But as long as we plug in the right numbers, we'll get the right result that we want. So that's our rotation. Quite often we want to use a positive and negative, and we can just randomize here. And because we've got this evaluation type spawn only, it will only calculate that once and won't keep recalculating. If this was set to every frame, it's now going to keep randomizing and jittering, which you may want. There may be something useful to that. But generally we want spawn only. Okay. That, I believe, is all the settings that we're going to go through for the sprite renderer. There obviously are other settings here as well. There's a lot going on, but some of these are more advanced, so coverage mode and these kinds of things. When we talk about sort mode, so depending on how we're sorting, let's do that in the next video. So we'll do a separate video about particle sorting. Okay, so we're just going to have to make a few changes to our module here to see the sort mode or the sorting differences. So I'm just going to get rid of this rotation, and I'm going to spawn, let's do a spawn rate instead, and just have an initial velocity as well. Spawn, let's see. Looks like a good number. Don't need to have the custom alignment. Now these are going to be a additive material, which isn't going to be very helpful for our sorting. Got some smoke. Well, maybe not the best example. And let's make a flipbook. That needs to be a 6x6. Hopefully that doesn't crash the editor. Does seem to have. Oh, no, there we go. And just disable the cutout as well. So very common, this kind of thing. The texture here, not the correct one. For this one, there we go. Well, it's going to be a bit tricky to see this as well. But anyway, we'll do the best we can, and we'll talk about what's happening and why. So set that down. So we have here a series of particles. They are sorting pretty well, but occasionally we get popping and we need to do some custom sorting to help that work better. And And that's what this one does here, sort mode. So by none, it will do no additional sorting. It will just kind of work out the best thing it can to render. But we can sort by view depth. So how far away or how deep into the scene are we is the particle, and so you kind of get the particles in front of other particles sorting correctly. View distance. So this is using the same kind of thing, one to the particles, one to the camera's origin and one to the camera's near plane. So that will make a slight difference to when we're very sort of close into the two things. And then custom ascending and custom descending. So custom ascending will always sort the latest particle, so the oldest particle. Here we go. Lower values will sort before higher values, and so one would draw on top of 0, and vice versa. So you can kind of do from the bottom and from the top. Not really seeing that at all in this texture, this material. It is a surface. Don't need substrate. It is a translucent. So maybe if I set the color a bit darker. I'm not really getting any sorting errors. Niagara's pretty good at sorting. Can't really create any errors here, but when you do get any errors, this is how you fix it. You can use the sort mode here. Okay, that is everything that I'm going to want to go through for the sprite renderer. Quick overview: we have a material that we assign up here. If we're using a flipbook, we can set the subimage size down here and use the subimage animation module. If we are using a cutout, we generally want to use a cutout to cut out the edges. We're doing that with various flipbooks, and we can set that here. We have sprite rotation, which can be just added as a module. And then finally, we have the sort of custom facing vectors and custom alignment. So velocity alignment, world facing, world up facing, those kinds of things are very useful as well. So that's it for the sprite renderer. In the next few videos, we'll be having a look at the mesh renderer and the various settings and differences we have when dealing with meshes instead. Okay, right, welcome back to another video. So this one, we're going to be having a look at the mesh renderer. So if we want to change our renderer, default obviously being sprite, the way we do that is by adding a new renderer here and deleting the sort of existing one. And as I said really earlier, the particle simulation is calculating the points and the data on those points, and then the renderers are just kind of like how we add what we're going to render and view on those points. So there's nothing stopping us having multiple renderers on the same point. Most common ones are going to be sprite and mesh. Maybe ribbon, we'll have a look at that, and then we'll have a look at some of these other ones as well. Some of these get quite complicated and more advanced things that we're maybe not going to look at in this course. But you have a lot of choice here, depending on what you want to do. So if you had a mesh renderer, let's just use a default one. It comes here with the Nomon mesh. It just takes any static mesh. No problems with it. Do be aware there is a slight overhead to using a mesh renderer instead of a sprite renderer. Even if you loaded in a plane that was 2 quads, the same as what the sprite would be, there is actually more of a cost to a mesh renderer, although it's not significant, so it isn't to say that you shouldn't use them, but there is actually a slightly more cost. So use sprites where you can, but obviously use meshes where more appropriate too. Okay, we can add multiple meshes here. So if we have the Nomon, let's just copy what we had before over here. So I've got sphere, shape cube, and shape cone. Shape cube and shape cone. Let's do this. So by having 2 meshes here, it's going to use the first one by default. So I'm only seeing my cube. And in the initialize particle, we can change the mesh renderer array visibility. So array being a data type with lots of entries. And so in this case, this is our array. You can see 2 array elements, our mesh array. In this case, we've only got 2 elements. but we could have as many as we like. And if we do a direct set and then tell it which mesh renderer to use, in this case, yeah, they've just got the same name. I don't know if you can just rename them. Maybe you can. My mesh renderer, that makes more sense. There we go. If you are dealing with multiple mesh renderers in the same system or the same emitter, probably makes sense to give them some names. And we can just do a direct set here. So mesh renderer, mesh index. It all gets a bit wordy, but basically it's saying which number here corresponds to which number here. Very useful. Allows us to do kind of like debris. If you were spawning a load of rock meshes, you wouldn't want one emitter per rock. That's how we used to work in Cascade times. Wasn't very good. We want to share that data. They're all going to move roughly the same way. The only thing that's different is the different mesh. And so the way we do that is by having an array of meshes here, and then we can choose from spawn like so. We can also do random. That will just randomize between any of the things that we have. We go cone, square, or cone cube, I should say. And that just works based on the size of the array that you have. So up to you how you want to do that. Cool. We looked at mesh scale before when we looked at the sort of introductory effects. This works as a multiplier. So instead of being in Unreal units, it's a multiplier times the scale of the mesh that was imported. And we do also have transforms in here as well. So we could scale our mesh up like so. So if I get my cube, why am I not getting a cube? Because I've set that to direct. There we go. And so I can scale my cube here if I wish. Cool. These are using the materials that were assigned to the static mesh. So if I open up the static mesh, there's the material assigned here, in this case, mbasic wall. If we want to override that, we obviously can. There's an option here for material overrides. And then if I assign it a material, debug UV Niagara, there we are. Now that's overwritten the material, and it will have done it for both of these meshes. So depending on how many material slots, what you want to override. And so, okay. That's probably enough for a quick introduction to the mesh renderer. Simply enough, apply meshes, apply materials, set sizes and scales. The one thing to remember with meshes rather than sprites is we have 3 items of data. If I do a non-uniform scale here, because it's a 3D object, not a 2D object, we have options for X, Y, and Z. Oh, my bounds are wrong, that's why that's flickering. There we are. So and that applies to obviously the size of the mesh and the orientation. Our rotations are now going to be in 3D instead of 2D, but we'll talk about rotations in one of the future videos. Okay, in the next video we'll start talking about well, orientations and rotations. Okay, so talking about mesh orientation. Now we have 3 axes with the mesh, and it can be a little bit confusing, but you can do basically everything you need to, just making sure that you've got the right things pointing in the right direction. So first thing we have here in the renderer, some facing mode options, same as with sprites, so we can face towards the camera, and we can make a camera facing mesh, which isn't very useful. Generally we'd use sprites for camera facing, but there's also this option for a mesh. But we can also do velocity aligned. So if I just add a quick velocity from point, we can see we get a burst. I've just put my spawn up as well. If you're only seeing one, that's why. And we get a burst of particles firing out, but they're not aligned towards their point. That would make more sense. The alignment here in facing mode is towards the x-axis of the mesh. Our mesh is modeled Z up. So we can just rotate it. So I think minus 90 in Z, is that right? Minus 90 in Y. There we go, minus 90 in Y. Just trial and error until that looks right. Or work it out either way. We can rotate our model. That's fine. We've got this transform here as well. So that's pretty cool. That works quite nicely. Yeah, so velocity alignment, and then it's the x-axis of the model. If you're making something custom, or if you're using something that exists, you need to rotate it. Well, you can do that in the transform of the mesh here. As well as the facing mode, we can also do an initial mesh orientation. So if I just disable the velocity for a second, the default for this is just random, and just random orientation, and you can see we get a random direction. That's nice, that's fine. We can do align to system, so that will just align to the system in the world. We have a look here, there it is. If I rotate this around and then reset it, that's going to move and just align with what's there. Reset that one, there we go. We can also do an alignment to a vector. So in this case, let's reset these values here. Disable that a second. Oops. Let's say we wanted to sample a static mesh. If I go in my particle spawn and static mesh location, put that at the top. What we can do, and let's sample a sphere of some kind. Material sphere. That in both here. We can see we're sampling the position. And also, in this case, the orientation sampling, so it's being applied to the model. That's cool. That's fine. This module also does both. It does the sampling, gets the data, and then also does the application. If we were getting a vector from somewhere else, or we wanted to do it ourselves, if we change this to just output in orientation sampling, what's happening is our initial mesh orientation aligned to vector is being aligned to the sampled normals. And there we go, and that's the sampled normals being applied. So we've got the mesh axis. I've left my rotation on, which is why this all works. If we don't rotate our mesh here, we can align our z-axis, which is our up. So it doesn't matter which you use, it's all just different transforms. But whether you align the mesh up to your normals or you rotate your mesh 90 degrees, doesn't matter, it's going to give you the same result. But that's a really nice way to work if you've got a certain kind of vector that you want your meshes to follow or point towards. That might be the, I don't know, the light direction, that might be a surface normal that you've calculated, could be a wind direction, anything like that could be quite useful for aligning your models. Cool. Orient to matrix, we won't go into that one. You can plug in a full transform matrix if that's something you want to do, and similarly orient to quaternion. Not something I've really used if you're doing with quaternion rotations, if that's a thing, but there are options there for you. With all of the orientation modules, we also have an option for rotation, and what that will do is it will rotate around the mesh axes. So in this case, if I want to rotate around Z, this is in a let's just turn on determinism so it's the same each time. This is in normalized rotation, so 0 to 1, so 1 being a full rotation, so 0 and 1 giving us the same result. But 0.5, you can hopefully see from the texturing, that kind of UV layout grid is quite useful. So if you want to do a rotation, a random rotation, we can do a random value between 0 and 1 in Z, and that's the mesh coordinate system, 0 to 1. Obviously it's deterministic, so it's going to be the same now, but hopefully you can see if I put this 0 to 0, all of the kind of texturing, all the lines are the same. In fact, if I just go to my mesh renderer, if I scale this so that they're, let's do that instead, shall we? So now they're not circular, they've been squashed. Now my rotations should be a bit more easy to see. So if I go to my thing here, if I turn this on, you can see they're sort of rotating around. So lots of control. With 3 axes, you kind of have to think, what's the primary axis I want to do? In this case, what do I want to orient with? And then how do I want to rotate around that primary axis? And so this is sort of your main pointing direction, and then this is your sort of secondary pointing direction. This tends to be the way that things are working. So cool. that's it for initial mesh orientation. In the next video, we'll have a look at the update mesh orientation to do some animation of our mesh and as they rotate and stuff. Okay, so if they spawning like this and we want to make them rotate, there's a couple of options we can do. We can do a update mesh orientation. That is sort of directly setting the orientation of the mesh, so similar to initial mesh orientation, but now it's happening in the update part, and so we can do animation with it. And we also have mesh rotation forces, and we'll have a look at that one first. So this is just applying a rotational force to our model. If we apply a force in Z, again, this is in the mesh coordinate system, so the fact that they're all pointing in different directions, we don't need to worry about that. We can do spin nice and easily. If we did want them to sort of rotate, they're in some kind of vortex, we could use a world space rotation. And now they're all rotating around that sort of global up axis. And similarly, we could do a local one if it was local to the simulation. Not going to be any different here, but if I rotate this object, now it's using the local, in this case Z axis. Let's turn that to local. There we go. So it's using the local Z axis to do our rotation around. And obviously here, if I change that to world, it's now using the world location, the world Z axis, regardless of the orientation. With a lot of these things, generally it'll be pretty obvious what it is you're doing, depending on the effect that you're making. You just have to think, is it local or world? Or in this case, is it in fact mesh? And we just want the meshes to spin on their axis. Cool. That's mesh rotation forces. They work quite nicely. Obviously, we can do randomness within this. We could do a random vector, let's say between 0 and 5 and -5, something like that. So some go one way, some go the other, some barely spin at all. Obviously, all the standard Niagara things. This is in the spawn, so it's being applied once when they start, and we can have a rotational drag to this as well. That would be in update. Drag, rotational drag. So I talked about rotational drag before. This is going to be reducing the rotational forces, and you can see there how they sort of slow down over time. It's very cool. Disable that for a second. Yeah, update mesh orientation. This works in similar way. So as I say, similar to the initial mesh orientation, we have options for rotation rate, orient to vectors, orient to position, and then flight and rolling, which are some interesting ones that we'll get to. So rotation rate, we're going to assign a vector to rotate around. In this case, it's going to be the up axis of the mesh, and then our rotation rate, so positive and negative. Well, or whatever we want really, and that's doing that spin. So either we're doing it as a force, or we're doing it directly by editing the value. So in the same way we looked at vectors and velocities, and then we looked at forces, these are the same kind of two things as well. So do we want to use a force to do it, or do we want to just set the value? Both equally valid, both have yeah, their own uses. Here, because we're updating the mesh orientation, it's not affected by the rotational drag. So you have to decide whether you're using forces or not, or whether you're doing it directly. But depending on what you're doing, it might be a better or worse way, but the end result is going to be the same or similar either way. Cool, that's rotation rate. We can also do orient to vector. So if we had an animated vector that we were sort of plugging in from elsewhere, and we wanted our particles to sort of follow that, maybe there was a, I don't know, an attack effect that's going to track you as you move, you want to plug in the player's position, those particles are now going to be updating and orienting towards you. That would be where you might want to use an orient to vector option, or in fact probably for that you'd use orient towards position, and you'd plug in the position you want to point towards. Cool. Right, flight orientation and rolling orientation. These are a little bit more specific. but they do some quite interesting things, and so we'll have a look at them in the next module. Well, one thing I will say just quickly, there's nothing stopping us using update mesh orientation and rotation forces at the same time. And so you can do kind of a thing that has physicsy spinning and also is pointing towards certain things. They aren't independent. They aren't exclusive. You don't have to worry just because you're using one or the other. You can use both. Some nice random spinning things. Cool. As I say, in the next video we'll have a look at the flight and rolling orientation.